Okay, so welcome to this session of QIP. We have one talk in this session, and we're excited to hear from Subhasree Patro, who's going to tell us about fine-grained complexity via quantum walks in some joint work that's with Harry Buhrman, Bruno, Loff, and Florian Speelman. So please take it away.
Hi, everyone. I'm Subhasree Patro, and let me begin my talk. Okay, there's a lot of money going into quantum computing, and rightfully so, because quantum computers are a more powerful model of computation than classical ones. However, quantum speedup is not guaranteed for all problems. Let's look at some example. For example, for problems like integer factorization and discrete log, we have quantum algorithms that are exponentially faster than the classical ones. But for problems like three-sum, CNF, SAT, orthogonal vectors, the quantum speedup that we have is just polynomial as of now. And for problems like longest common subsequence, edit distance, or parity CNF SAT, we don't even have any quantum algorithms that are faster than the classical ones. So we would really like to know for what kind of problems quantum speedup is guaranteed, and if at all it is guaranteed, by how much speedup is guaranteed. Okay, the state of the art is not too bad. For example, for problems like unordered search, we know that the quantum speedup that we get is optimal. But for NP-hard problems like traveling salesperson problem or CNF SAT, the speedup that is not known to be optimal. And in some other cases, for example, like the recommendation algorithms, we thought we had an exponential quantum speedup, but it then turned out that we did not. So again, the question is, how much quantum speedup is possible? And there was this recent result by Babush et al., where they showed that with the current error correcting techniques, there is no quantum advantage for problems which have only quadratic speedup, especially when we consider practical input sizes. But how do we assert that a speedup that is given for some problem is just at best quadratic? And we will do that by proving lower bounds. There are these several computational geometry problems for which Ambainis and Larka in 2020 gave quantum algorithms that were quadratically faster than the classical ones. And using our techniques, based on some certain reasonable conjectures, we show that this is the best that we can do, and any further speedup is not possible. Hence, for people who are interested in solving computational geometry problems, it is advisable not to use quantum computers for that unless there is some significant improvement in this error correction techniques. And we prove these results by using a family of techniques called fine-grained complexity. Okay? But I should also point out that similar results have been, there's a similar quantum fine-grained results have been also proven for other problems such as closest pair problem or biochromatic closest pair problem. This was a paper by Aronson et al. In 2020. And similar results have been also given for string comparison problems like edit distance or LCS by Buhrman et al. In 2021. I was also an author in that. Let me also clarify, because I'm going to use this term upper bound and lower bound a lot in my talk. What we mean by upper bound and lower bound in complexity theory is an upper bound for any computational problem is the amount of time taken by the best known algorithm that solves the problem. And lower bound, on the other hand, is the time required by any algorithm that solves the problem. And we say the bounds are tight, or we say we have an optimal algorithm if the upper bound and the lower bound matches for that algorithm. Okay? But we do not know how to prove unconditional lower bounds. So we resort to a technique called fine-grained reduction. Okay, I'll just briefly state what this is, what this looks like. Imagine you have this problem A that people have tried to solve, and they've tried to come up with better and better algorithms, but they are not able to improve on the algorithm of this problem. And then we have another problem B, which is also a interesting problem, but is not as well studied as problem A, suppose. And can I then comment on hardness of problem B based on the hardness that I know of problem A? I can, if we can have a reduction from problem A to problem B. And what I mean by reduction, if we can solve problem A by using the algorithm of problem B, then we say there's a reduction possible from problem A to problem B. Now, how is this going to help us? This is going to help us because if there was a fast algorithm that can solve problem B faster, then we can solve problem A faster by using that algorithm. But we don't believe that problem A can be solved any faster, which means there shouldn't be a fast algorithm for problem B, which means we have concluded a lower bound for problem B based on a lower bound that we believe is true for problem A. And for the purpose of this talk, my problem A is going to be the three-sum problem, which I will discuss quickly. And we conclude lower bounds for computational geometry problems and another graph problems called as zero-edge weight triangle finding problem. Okay. Now let's look at the three-sum problem. It's a very simple problem to describe. We have this list S of n integers, and all we want to know whether or not there exist three elements in the set such that their sum is equal to 0. Okay. Now, for example, this is a list with 6 integers, and we do have a solution here. We have 3 elements that add up to 0. Now, what is the classical complexity of this three-sum problem? Now, clearly, we have an n-cube algorithm where you just go over all these n, choose 3 triples, and you check if there is a solution or not. But there is also a slightly less trivial n-squared algorithm, but I'm going to discuss an n-squared log n algorithm. And for the purpose of this talk, we are going to ignore any polynomial factors, any polylogarithmic factors to this problem, okay? So you have this input to three-sum, you make a copy of it, and then you make a third copy, which is sorted, okay? Now that takes you order n log n time to do this. And now you go over all these n square pairs, you see their sum and check if sum of any of these n square pairs exists with a negative sign in the third list. And because the third list is sorted, that gives you an overhead factor of log n, which means you can solve this entire three-sum problem in n square log n time, okay? Now, people try to improve on this n square log n time. We could actually make this algorithm also take n square time. And people have come up with even polylogarithmic speedups to this n square algorithm as well. But there is no strictly subquadratic algorithm known for this three-sum problem. And consequently, it was conjectured that three-sum requires n square time on a classical computer. And based on this believed hardness of three-sum in the classical setting, lower bounds were given for a lot of these problems. There was a vast collection of computational geometry problems, the zero-edge weight triangle finding problem, matching triangles, and so on, okay? And this kind of explains why people are not able to improve on the existing algorithms for all these plethora of problems here, okay? Now, let's zone in a bit on this reduction from three-sum to zero-edge weight triangle finding problem. Now, this reduction was a classical reduction given by Virginia Williams et al. And what they showed is if there exists a subcubic algorithm, zero-edge weight triangle finding problem is a graph problem of where we have nodes and we have edges, but we also have weights on these edges. And all we want to know whether there exists a triangle whose sum of the weights of the edges add to 0, okay? Now, what they showed is if there was a subcubic algorithm for this zero-edge weight triangle finding problem, then they gave a reduction such that we get a subquadratic algorithm for three-sum problem, which we do not believe under this classical three-sum conjecture. That means there shouldn't, like even the zero-edge weight triangle finding problem should require n-cube time. Now, what was interesting was this reduction went through actually a tiny step where they kind of sort the input, not like it takes like linear amount of time, a simple sorting, structuring of this input of three-sum. And then they gave a non-trivial reduction from the sorted version of three-sum to this zero-edge weight triangle finding problem, okay? Now, what was more interesting was that even the other reduction, the reduction from the classical reduction from three-sum to these computational geometry problem, also went through a similar step where they sort the input to three-sum and then they reduce to the other problems. And the sorting part is obviously trivial. What was creative was this reduction from sorted three-sum to these computational geometry and sorted three-sum to this zero-edge weight triangle finding. Now, but we care about quantum. We are quantum people. So let's now let's understand what happens to these reductions in the quantum setting. Now let's first understand the hardness of three-sum problem itself in the quantum setting. Now, remember, recall this n square log n algorithm that I just briefly mentioned before. Now we can speed up this n square log n algorithm in the following way. Now we make a copy of this input, a sorted copy, which will take us n log n time. But now, instead of, we will go over these n square tuples again in the similar way that we did it in the classical setting, but we're going to use Grover search over it. So we get the speed up, and so we have this n log n quantum time algorithm to solve three-sum. So obviously now, this classical three-sum conjecture no longer holds in the quantum setting. But people tried to improve on this, and there is no improvement has been seen in this quantum setting. Like no sublinear three-sum algorithm is known for, no sublinear quantum time algorithm is known for three-sum. But now what happens to all these reductions that, the classical reductions that have existed in this, what happens to them in the quantum world? Do they still go in the similar way, like from three-sum to sorted three-sum to these corresponding problems? Now, what we noticed was the classical reduction from sorted three-sum to this computational geometry or the zero-edge weight triangle were actually easily quantizable because the reduction had some local property that we could just quantize. But we could not, however, reduce three-sum to sorted three-sum in the quantum setting because we do not have a sublinear quantum time algorithm to sort. So this whole classical thing kind of fails here. So we try to understand what is the hardness of sorted three-sum in the quantum world. Now, what I mean by sorted three-sum is three-sum problem with a promise that the input is sorted. What if this is faster? So we wanted to actually understand the hardness of sorted three-sum. So for that, and this becomes the crux of our paper, because so what we do is we try to look at the we give a hardness result for sorted three-sum by actually looking at the quantum query algorithm that solves three-sum problem. Okay, so let's recall the quantum query algorithm that solves three-sum problem. This algorithm was actually originally given by Ambainis to solve element distinctness, and then it was observed by Andrew and et al. That it could solve a little more general class of problems, among which three-sum is one of them. Okay. Now this query algorithm is a walk on a Johnson graph parameterized by n and r. And what does this graph look like? We have a graph of n choose r vertices, where each vertex on this graph represents an r-size subset of the input to the three-sum problem. And we have nodes connected to each other if and only if the nodes differ in exactly one element. Okay. Now we say the nodes are marked if it contains solution to the three-sum problem. And the walk algorithms, the job of the walk algorithm is to find these marked nodes. And it was shown that in n power 3 by 4 number of queries, we can actually find a solution to the three-sum problem. And the complexity of this walk algorithm can be actually captured by using, by this formula, where S is the setup cost, like the cost of setting the initial state of this walk algorithm. C is the checking cost, where checking cost implies the checking cost is the time, number of queries in this case, required to check if a node contains a solution or not. And U represents the update cost, where the update cost means like if I'm walking over this graph, right? So every time I change from one node to another node, to a neighboring node, that's the update cost. So it was seen that we can actually reach this optimal query algorithm with S set as R, with 0 checking cost and with update cost being 2. Now, but what happens to what is the time complexity of this algorithm? Okay. Now, it turns out that we can use the same, the time complexity also can be captured by the same formula. It's just that there exists methods where we can make the setup cost slightly worse. So just with polylogarithmic factor of R, update cost also slightly worse, but we do not have a way to actually make the checking cost small. Okay. So this, that's why we don't have a sublinear time algorithm for threesome. But now, what if we are able to actually store the elements in these nodes in such a way that, in a structured way, that I can reduce this C cost, okay, the checking cost. Now, what we noticed, there are these dynamic data structures that we can use to store these nodes in, store the elements of these nodes, which has polylogarithmic insertion, deletion, and indexing cost. And using these data structures, we are again able to achieve the setup cost as almost R, update cost as almost 1. And now, if there was a faster algorithm for sorted threesome, suppose, imagine there was a sublinear quantum time algorithm, then we could use this algorithm to actually check for the solution, because now we have all these inputs in these nodes in a sorted order, right? So plugging in those values as C being a sublinear time, a sublinear in R time algorithm, we actually get that threesome can also be, the total cost can be made sublinear, which means by assuming that we have a sorted threesome algorithm which is fast, we are getting a faster threesome algorithm in the quantum setting, which we do not believe to be possible under this quantum threesome conjecture. So therefore, what we notice that if we believe that threesome requires linear time, then sorted threesome also must require linear time on a quantum computer. And using the same technique, we were also able to comment on hardness of a little different than sorted, but other structured version of threesome problems. Okay, and that became the main result of our paper, where we were able to comment on the hardness of sorted threesome based on the hardness of threesome, which was not easy to quantize. And because of that, we were able to give almost tight bounds for most of these computational geometry and tight bounds for this zero edge weight triangle finding problem. And now to summarize, we believe that fine-grained reduction is a promising way to prove superlinear lower bounds or lower bounds which are beyond query complexity regime. Okay, and using our proof strategy, we were able to comment on hardness of certain structured versions of threesome, which we feel are novel ways to do it, especially given that we cannot sort an input in sublinear quantum time. And we observed, based on all these results, that for many computational geometry problems, more than quadratic speedup is not possible. And we feel there are many future directions to this project. To begin with, some low-hanging fruits are there are so many other classical reductions from threesome to, say, sequence problems or dynamic problems, triangle collection, matching triangles, which are still open. And maybe we can even get lower bounds, tight lower bounds for those problems. And there are also certain computational geometry problems. I don't know if you can see the cursor, but say triangle measure or these planar motion planning, where the bounds that were concluded are still not tight. So maybe we need to understand the hardness of some other property of threesome, or maybe we need to come up with better algorithms. So there's still an unexplainable gap that we have to bridge there. And we feel quantum fine-grained complexity opens a interesting way to prove conditional time lower bounds, because unlike threesome, maybe you can use CNF-SAT like we have done in some other papers, or some APSP, some other key problems, and give lower bounds based on hardness of those problems. And this is my talk. But before I thank, I need to advertise. We have 2 tenure track positions at QSoft, and you can check out all the job details in this website. And the application deadline is 1st of April. And apart from that, there are a lot of PhD and postdoc positions as well. Please check the website because the deadlines are somewhere in March and on different dates of March. Okay. Thank you for your attention, and I'm ready to take questions now.
Thank you. Thank you very much. This was a really nice talk.
Thank you.
Thanks for telling us about this work. So it looks like, as far as I can see, there are not questions in the chat just yet. I also think there's a little bit of lag maybe between the sort of the live talk and the streaming. So if you have questions, please feel free to put them in the chat. But maybe, yeah, I don't know, maybe just to kick things off, maybe I can just ask. So, I mean, this is maybe kind of an obvious question, but what happens when you look at sums of more than 3 things? I mean, is this problem sort of, you ask about sort of like 4 sum or something, I guess both classically and quantumly, is this interesting, or is sort of everything that goes on already captured by the 3 sum case? Is there anything there?
So for like say general case sum problem, though we have sublinear query algorithm by the same, I think your paper actually, yeah. But the time complexity there becomes a function of k there. I'm exactly not sure whether it is k by 3 or k by, it's a function of k. But I don't know if there are reductions from k sum. I have not looked at any classical reduction from a k sum problem to other thing. But I'm sure that will be also interesting to look at.
I see. Okay, thanks. Yeah, maybe I can also just ask if there's, you mentioned a lot of open questions. I mean, it does seem like this is a potentially very fruitful area because you've done a lot, but there's also a lot to do. Do you have a sort of a favorite direction? I mean, of all the questions you mentioned some motion planning problems and some other things. Do you think there's something that's, especially important or just mathematically interesting to think about?
So yeah, there are these certain problems that that go. Okay, so we are basically now looking at some reductions from other key problems. Like we have looked some reductions from CNF-SAT. This was 3 sum next. We are looking also from some other key problem reductions. And there are certain problems that are reduced from all these key problems. And we are actually trying to understand the hardness of those problems as of now. I think we should be able to get the results out in some time.
Awesome. Yeah, looking forward to seeing it. Okay, well, I don't see more questions in the chat right now, and I guess we want to make sure people have time to get to the next talk if they're interested in going there. So there's not an additional talk in this session, but I think there is another talk happening in another session. For anyone who plans to go there. So maybe let's just thank Subhasree again. So maybe I'll just on behalf of the virtual audience, I will thank you. Thanks for attending. And I should mention that there's also a separate Q&A session where we can have maybe a little more interactive discussion. There's a 20-minute session on Zoom. You can find the details for how to get there on the conference website, and that'll happen in another 25 minutes from now. Whatever time zone you're in, it's about another 25 minutes from now.
Thank you.
So thanks very much. Thank you.